So it is my pleasure to be here for this symposium in the memory of Xavier Le Pichon, and I try to see how I can connect this, and I found this work, this section of a book which was given here, talking on the adoption of a scientific theory with plate tectonic and a greenhouse effect. And there is the introduction of that work. Why I think that this is an important point, because if we compare planets, as it was made by Alessandro, it is obvious that greenhouse and plate tectonics is something where we have the beauty of comparative planetology. We have on one side Venus, where the greenhouse is infernal. We have on the other side Mars, where the greenhouse is very tiny. We know in all the cases that the Earth was able to trap CO2, even if in the last decade, it is not able to trap it anymore as it was in the past. But most of the CO2 trapping is generated by plate tectonic. On the opposite, most of the CO2 generation on geological scale was generated by volcanism. And on the two sides, you have a planet with a very weak volcanism, Mars, and you have a planet where you have a very strong volcanism, Venus. So therefore, we see that everything is coupled. Volcanism from the origin of CO2, plate tectonic as a way to trap on geological scale. And then we have the moon, which is around Earth, which is also unique for all these planets. We know and accept that the moon are a result of the collision of Theia, something like 4.4 billion years ago. And therefore, we have to ask ourselves, is the moon also related to plate tectonics and to the habitability of the Earth? Because there is no moon on Venus, there is no such big moon on Mars. So therefore, we cannot see the Earth, plate tectonics, greenhouse on the Earth without having a look on our planets. And the moon as, the remaining piece of the bullet, which was a very big bullet, by the way, which hit the Earth 4.4 billion years ago. And as said, I do believe that the answer to this question is in the internal structure of the planet, because it is the way these planets are generating volcanism, may generate plate tectonics. And I do believe that it is also in the structure of the moon, because the size of the core, the temperature of the moon is basically only what is left today from that impact and from the geometry of the impact of Theia on the proto-Earth. So therefore, I think that maybe if Le Pichon was today there, he will also advocate that the next step is, indeed to go in other planet to understand all the piece of the puzzle. So, as said, this is done for internal structure by seismology. I will not go on everything. I will focus on insight. So, what is really very important for us and for you to understand is that insight was made at a time when everybody on the two sides of the Atlantic were very happy to do international collaboration. I do believe that insight will never be possible today. I think that it was really huge opportunities on the French side, because we have got a very strong support on the national European side. and on the US side. And as you know, we got troubles, we got issues, we had to delay the mission, and the two sides of the Atlantic were able to get consensus to continue the mission. So therefore, I really want to thank the CNES of that time, and also the NASA of that time. And I do believe that many people at NASA, at CNES, want to continue, even if there are a lot of pressure from politics world. Anyway, it was also a beautiful team mission. So I am just here, presenting the results of all the team. And for me, it started a long time ago, in '93. I was here, testing the windshield. And at the end, the windshield of InSight was very close from what we tested at Pinion Flat Observatory in the '93. So it was a very complex instrument, the seismometer. It is not a seismograph. Seismograph is something which is writing, the record, but it was a seismometer, providing output in digital data. It was a 24-bit instrument, very sensitive. So basically, the sensitivity, is comparable to the gravitational attraction of your mobile phone when you are 10 centimeters away from your brain. So therefore, this is more or less the sensitivity of the instrument, about 10 minus 10 meters second square per square root of Hertz. And here you have the movie of the deployment, which looks super nice. You have the feeling that everything is done very rapidly, but it was done, in fact, in 3 months. And this shows also that, yes, robotic missions are very nice, but they are very long. And, on the moon, the deployment of the seismometer by the astronaut was made in 30 minutes, 40 minutes. So here, 3 months versus 30 minutes. So when we land on Mars, the big question mark was the seismic noise. Why? Because you have here this record, which is a little bit complex to interpret, but I will take a few minutes. So here you have the frequency, so from 100 seconds or 0.01 hertz up to 50 hertz here. And here you have the acceleration level. So this is 10 minus 10, okay, which is our peak sensitivity there at something like 1 second. And the color here are the probability for the Martian noise to have that value. And then you have many other curves on this figure. The first one is this, these two curves, which are associated to the Earth's microseismic noise. And you see that between there and there, we have 3 orders of magnitude. 3 orders of magnitude means that we have about 2 magnitude of quake. And therefore, we can, with one station on Mars, detect quake with a magnitude 2 units lower than what we do on the Earth. Typically, on the Earth, we detect magnitude 5. We can go down to magnitude 3. Second point is that you have this red line. This red line are the noise we got when we were on the deck of InSight before deploying the seismometer. And you see that this explains why Viking was not able to detect something. And this also shows that if we had had any problem during the deployment, I will not be there today to explain you that we got a lot of results. So therefore, the key point is that because of that very low noise, we have been able, with one seismometer, to listen about half of the planet in terms of seismic activity. So the first quake was detected in May. So therefore, in May, meaning almost 7 years ago, okay. It was detected in May, 8 years ago. No, 7, sorry. It was detected in May 2019. And this came from a location called Cerberus Fossé, on which I will discuss a little bit. And then we got our big one, our big one was, at the end of the mission, it was a magnitude 4.5, 4.7. There are still question marks on this. And here you have, the signal of this big one. So here you have a collection of all the quake we detected, for which we have been able really to use all the quake information, P arrival time, S arrival time, sometimes surface wave, in order to make a model of the interior. Okay, first, before to discuss on the structure, I want to say a few words on the seismicity. I do believe that probably the first discovery we made with InSight was to detect a location on Mars where there is today seismic tectonic, an ongoing seismotectonic process. And this is Cerberus Fossé. And I will explain you why. So we detected about, 1,300 events, with this magnitude range, from 0 to 160 degrees of epicentral distance. But you see that there is a big cluster of quake here, and all these quakes are coming from Cerberus Fossé. And this is shown on this figure. We have a lot of quake coming from there, something like 3.5 up to between 3 and 3.5 in magnitude. We know that on this location we had volcanism in the last 500,000 years. And therefore Cerberus Fossé is a location on Mars where every month you have a 3.5 quake, where you had volcanism, active volcanism in the last 500,000 years, meaning that it is not stopped there. There is something ongoing. Sometimes when I do a lecture to the public, I say, okay, if you go to Clermont-Ferrand, we know that the volcanoes were active a few tens of thousands years ago, but you don't have magnitude 3.5 quake every day in Clermont-Ferrand. So therefore, Cerberus Fossé in some way is more active than the Central Massif in France. And really this, for me, is one of the big discoveries we made, because it was not clear to us that we will see active tectonism, ongoing one, on Mars. Now, with all this quake, we have been able to record the P wave, the S wave. But as you understand, when you have the P and the S, two data, the only thing you can get is the time of the quake and the distance of the quake for a given model of the interior. So therefore, in order to do something more than locating the quake with a given model, we need to get something else. Okay, the something else where what we call this bouncing wave, what the seismologists call PP, PPP, or SS, SSS. These are waves bouncing one time, two times on the surface of the planet before arriving to the station. And as you see on this figure, the direct wave is this one, for example. And this is what might be a PP or SS, and this is what might be a PPP or SSS. But you see that more the wave is bouncing, shallower the wave is propagating. So therefore, the key point is that the record of the arrival time of this wave, the PPP, the PP, and the P, will tell us on the vertical gradient of the velocity in the interior of the planet. And this is almost, the Graal for us, because this gives us immediately the measurement of the thermal lithosphere of the planet, which is a key parameter for, the cooling rate of the planet. So therefore, we have used this. And also, we have used bouncing wave on the core, which give us the radius of the core. So therefore, this was possible to go to this detail because we have been able really to get much more than the P and the S because of the quality of the instrument. Okay, now what we did is, like on the Earth, we start with the top and we go to the bottom. So when we start to the top, we are using the wave rising up, and this wave will be converted when they hit the MOHO of Mars, and therefore you see we will have a differential arrival time between the primary wave and the converted wave. And this gives us information on the distance between, or if you prefer, the travel time between there and there for two types of wave, a PS and a S wave. And on the top of that, the amplitude of this phase gives us information on the impedance contrast, so meaning, something related to the velocity and to the density. At the end, seismologists call this receiver function analysis, and this gives us a way to predict and to determine the model of the crust below the landing site. And at the end, we found a crustal thickness of about 40 kilometers below our landing site. So then we have tried to use other waves. We have been very lucky at one time to get a very big quake, this magnitude 4.4, where you have here the record, you see a very, very long coda of the wave, meaning that, the wave are not propagating directly from the station to from the quake to the station, but they are diffracted in the structure. This is really a unique signature for such a quake. On the Earth, we do not have that long coda. And on this wave, we have been able to detect the surface wave, which gave us additional information on the crust between the quake location and our station. Now, I go to this, and also we get information on what we call anisotropy, but I do believe that this anisotropy is mostly resulting from the fact that in the crust we have a layered structure, which is making the wave vibrating horizontally like this, better life than those oscillating vertically, which are the Rayleigh wave. But again, you see, it gave us information on the crust and also on the bottom crust, and very likely we got to the conclusion that crust have big layers, so meaning that there is a complex geological history to make that crust compared to a very simple crust process where everything is homogeneous. Now, when we have the crust, we can go deeper in the mantle. And here, again, the idea is to use this direct wave, P wave, and the PP or the PPP. So, and basically, the idea is that you can retrieve the shape of the direct wave in the late arrival. And on this example, this is the S wave, and we end up to the conclusion that our SS wave is there. And therefore, this differential travel time gives us the difference of propagation time between wave propagating at this depth and wave propagating at that depth. At the end, when we couple this to a mineralogical model of the planet, we end up to this very nice determination of the gradient of the planet down to a depth of something like, you see, so here we have a first gradient here, down to something like 500 kilometers, and here we have the P velocity in the mantle, and here we have some possible transition zone. But it is very important to keep in mind that because we have only one station, this is not like PREM. These are models which are still, I would say, sensitive to the hypothesis we do for the mineralogy. And indeed, if we wanted to invert only the seismic data without any, I would say, information on the mineralogy, we will have a much more, noisy inversion of the structure. So therefore, it is very important here to couple this with the interior information. But at the end, the seismometer was able to determine the thickness of the lithosphere. And when you get the thickness of the lithosphere, you almost immediately get the heat flow of the planet. So therefore, even if on InSight we had a heat flow measurement, we have been able to make it because of that measurement, and therefore we have been able to determine the heat flow of the planet, even with the seismometer. And now, we go to the core. Okay, the core was a very remarkable achievement of the team. It was published in Science, and we got that prize, which is given to the best science paper of the year. And we donate, by the way, the money to Médecins Sans Frontières after the quake of Turkey, I guess, because it was the year of that quake. That work gave us the radius of the core to be about 1,830 kilometers. It was confirmed by other study, outside the team. But to be fair, at that time we thought that was the core. In fact, that was the discontinuity between a solid something and a liquid something. And we thought that the solid something was the mantle and the liquid something was the core. You will see that it was not, in fact, possibly the right interpretation. Okay. Now, deeper, this is also the beauty of international collaboration and also to dissemination of the data. Recently, last year, a Chinese team made the proposal that there is an inner core on Mars, and that inner core is associated to this seismic phase, which were detected, which are clear in the data, and that work was made possible because of the diffusion of the data to the international community. Of course, when we have seen that paper, we told us, okay, why them and not us? But sometimes, when you are in a project, unfortunately, you do not have all the scientific team, able to work only on the data. But this shows also that there is a lot of work which was made outside the team. Okay, and last but not least, we also made this multiple surface wave observation and possibly normal modes, which are not yet confirmed, on which we need a lot of work. Okay, I will finish. I guess I have about 10 minutes. So I will finish with other observations which are not all related to the internal structure, but which are important. The first one are impact. Impact are very important because okay, so this is a movie. Impact are very important because when we are able to locate the impact, we have immediately the distance, the position of the quake, and therefore, by measuring the differential travel time between P and S, we can do inversion of the structure without any hypothesis on the location of the source. If on the top of that we have the time, it is even better because then we can just use the P and the S arrival time. So, and Rafael Garcia will do the talk on the moon after me, but he had a big role in this first paper where we detected after a signal, this very strange wave, and you hear them, maybe I will restart this. Okay, so you have the feeling that you have some fish in my computers. But in fact, because the team of Rafael made some simulation before the mission, they were able to understand rapidly the origin of this wave as being acoustic wave propagating at the surface. And because we know exactly the CO2 composition, we know therefore the velocity of the acoustic wave, and because we know that these acoustic waves are pure longitudinal signal, we have been able to determine their direction. And then we requested NASA satellite to take a picture of where we thought that the impact occurred. So this was the picture before the impact, and this was the picture after our request, where you see clearly, you know, 3 new craters, which are explained by the fact that we get 3 signals. The first one is mostly the entry of the impactor in the atmosphere. The second one is the airburst associated to the disruption of the impactor, and the last one are the one of the impact on the ground. So with this, Mélanie Driot, others in the team have been able to determine a very precise model of the crustal structure near our landing site, which is more or less close from what I have shown you before with the receiver function analysis. But on the day of Christmas 21, we got a huge signal. You will have here, you see, and this is that signal. Again, it was sonified. So this is the P, and this is the S, you know. And that signal was about magnitude 4, and our colleague from the Mars Reconnaissance Orbiter went back to their data, and they found about 3,400 kilometers away a huge crater with a diameter of 150 meters there. So, and this observation is the largest crater never detected by a seismometer since the start of seismology, because the largest one on the Earth occurred at the beginning of the 19th century in Saudi Arabia, at a time before, you know, the start of deploying a seismometer. To be clear, you know, we got a lot of airbursts on the Earth, you know, Chelyabinsk, etc. But all this, I would say, impact were not associated to impact on the ground. They were associated to airbursts in the atmosphere. So therefore, this was a huge crater, about 4 or 5 kilotons, you know, almost 7 kilotons in terms of energy, and it was almost like a nuclear explosion with a known location, and which gave us beautiful data. So we learned a lot from this. The first point is that by recording the rupture time of the shock wave in the ground, we were able to see that that rupture was propagating much faster than the impact close to inside. And why? Because you see, we need to have 400 meters per second instead of 300 meters per second. And in fact, the reason is why, because we have seen ice, which was excavated from the regolith, and therefore, you know, the shock wave did not propagate in dry regolith, but in icy regolith, for which there is a much larger seismic velocity. So this will be used on the moon to search for ice, I hope, in the near future. Second thing is that we have been able to detect something like 6 hours after the impact, another wave, and these are again infrasounds, but that time, you know, these infrasounds, they are bouncing in the thermosphere of the planet at 100, 250 kilometers of altitude, and they bounce, you know, 6 times before arriving to the station. And therefore, this shows us that, you know, even at long period, we can capture all the signal. And the last point is Henri Samuel, who will make a presentation later, I guess today or tomorrow, found that some of the seismic phase, you know, we have, okay, here you see that we have all the model we had, so we can explain very well the P wave, we can explain very well the S wave, but we cannot explain the PKP phase we recorded from our model. So meaning that there is something wrong, or we had something wrong in our model at that time at the base of the mantle. And the proposal which was made by Henri is that at the base of the mantle, we do not have a liquid core, but we have a liquid layer of silicate. And therefore, you know, this planet is very different from the Earth. It is a planet where we have a solid mantle, we have a liquid mantle, and we have a liquid core and possibly a solid inner core. So therefore, honestly, in 22, when we made our paper, we were pushed by the view of the Earth. And I think this is very important in science, is that, you know, when you go to other planets, you have to accept that this other planet will not be like the Earth. Okay, so this is my conclusion. So this is the figure, which might be in a high school textbook, on the composition of the planet, you know, Earth, Mars, Moon, seen by seismology. This was before InSight, and after InSight, we have been able to first propose that model, you know, and now we have this model, and probably, unfortunately, it will stay like this, at least for maybe 5 years for Mars, and I hope only a few years for the Moon. Okay, so I will conclude here, and of course, the conclusion is more on what next. Okay, the first point is that all the data are there, you know, you can use them, you can invite a student to work on them, everything is free. But what are the direction for the future? The first point is that we landed on a place where we had very poor coupling to the ground, not because of the coupling of the instrument to the ground, but because of the poor quality of the ground. So in order to do much better, we will need to be on bedrock. And therefore, if there is a next step, I will recommend that the next step is that we take the seismometer on the rover and we put it where we believe there is some bedrock. Now, the second next step is we had a very good seismometer with a very broadband seismometer, and what will be next? The next will be the Moon. We have one of the spare units of the seismometer flying to the Moon on the far side seismic suite. Raphael will develop that more in details. We still don't know exactly the launch. It might be around 29. NASA decided to cancel the launch contract with iSpace because iSpace put that launch in 2030. So therefore, we hope that it will be launched before. And I am not betting, but I can imagine that it will be launched on one of the Blue Origin lander preparing Artemis. And to make the link of Artemis, a second one has been proposed to NASA. The selection was made in fall 28. Very recently, you know, in April 25, CNES 26, CNES recalled that, you know, this seismometer will contribute to the Artemis 2 project. But recently, CNES told us that there is no funding for that project selected by NASA, which cost about 5 million euros, which means a big ERC. And it is today at cancellation risk, and we hope that CNES will change, or other partner will take the opportunity to go to the Moon to deploy seismology with astronauts and to deploy a seismic network on our satellites. Thank you.